we're going to look at this idea of mathematical induction. It's another way of proof. Now, of course, you're used to proving things by deduction most commonly. And that's why we call it deductive geometry, because you deduce a solution. This method of proof is where we induce a solution. Right? So I don't want you to just rote learn, if you like. Oh, and I know I've written it down as step 1, step 2, step 3, but it's an idea. Induction is an idea of way of doing it. But yeah, there are some steps that you go through. So the first idea is, well, look, I'm going to prove it true just for the first case. Usually that's going to be n equals 1, but be careful. Sometimes they might ask you to prove it true for even numbers. And in that case, it'd be n equals 2 would be the first case, or it might be numbers greater than or equal to 5, or whatever. So make sure, but usually it's n equals 1. Then, what we do in induction is we actually assume what it is we're trying to prove. We assume that to be true. And we do a simple thing. We just say, well, we'll let n be any number, so we just let it equal another pronumeral. So, oh, well, we'll let n equal k, where k is some... In most cases, it'll be a positive integer, but again, it just matches the question. If we were proving it true for even numbers, then I'd assume k is an even number and things like that. Then we go and prove it for the next case, k plus 1, or if it was an even number, k plus 2, whatever the next case would be. Of course, our proof hinges on our assumption being correct. And so when I finish my proof and I go, oh, you little beauty, I've got it, this statement I feel is the crux of the whole thing. And that's why it's important to say it and say, yeah, look, I have proven it, but my proof will only work if my assumption's correct. So a way of saying that is you say, oh, well, hence this is going to be true for k plus 1 if it is true for n equals k. Because then you go back to step 1 and you say, well, hang on though, I just proved it was true for n equals 1. So if I just proved it's true for k plus 1 if it's true for k, well, I know it's true for 1, therefore it must be true for 1 plus 1, 2. Well, now I know it's true for 2. So therefore it must be true for 2 plus 1, 3. Well, now I know it's true for 3. And that's what's called inducing the proof. We can now say, well, I don't have to work it out for every integer. I now know that it will work for every integer. And by the way, in that last step, you don't write this big essay out where you go, like I just did, oh, it's true for 1 plus 1, therefore 2. It's easy enough to say, well, look, hang on, since it's true for 1, then it must be true for all of them simply by induction. I'm going to induce that solution. The reason this is in the topic of series and sequences is because the first type of induction problem usually involves series. Yeah, we have a formula for arithmetic series. We have a formula for geometric. But of course, not all patterns are arithmetic and geometric. So the first use of induction is to prove a formula for other patterns. And so this pattern is the odd numbers squared. And we're saying, look, this formula for the sum would be 1/3 n, 2n minus 1, 2n plus 1, and that's what we want to prove. So, okay. Step 1. By the way, you don't have to write down step 1, step 2. I'm just saying, okay, our first step. But I would write down, prove the result's true as n equals 1, because it is a proof. You want to explain what you're doing. Now, this is the rare occasion where I do write left-hand side and right-hand side, because I'm going to substitute into both. So on the left-hand side, basically we're talking, hey, what's the first term? There's my general term, 2n minus 1 all squared. So when n equals 1, that's 1 squared, the first term. And we know that equals 1. Okay, let's sub it into the formula, and yes, we get 1. So the formula does work for the first case, if we simply had one term in this pattern. So, yep, left-hand side, that does equal the right-hand side. So, yes, I know that is true. It does work for the first case. So now I'm going to assume what it is that we're trying to prove. So I'm going to assume it's true for n equals k, where k is a positive integer. So really all I do is I rewrite it out, but instead of using n, I write k. Okay, there's my assumption. That it's going to be true. I then want to prove it's true for the next case. So everywhere I see an n or a k in the second one, I'm going to replace it with k plus 1. So the next term, if I sub k plus 1 in there, I'd get 2k plus 2 minus 1, which is 2k plus 1 squared. And on the right-hand side, instead of k, I got k plus 1. Instead of 2k minus 1, I'd end up with 2k plus 1. Instead of 2k plus 1, if we sub k plus 1 into that, we get 2k plus 3. That's what we want to prove. Now these series type, we do them pretty much the same way, in that what we do is we write out the left-hand side. Well, here's the series. But then I rewrite it, just highlighting that, hang on, what it is my assumption, which was those terms, plus the next term. Because then I can say, well, I've assumed that 1 squared plus 3 squared plus 5 squared up to 2k minus 1 all squared, I've assumed, if you like, the sum to k, and we're adding the k plus 1th term, but we've assumed that is 1/3 k, 2k minus 1, 2k plus 1, and I'm just adding the next term. Now I've got a piece of algebra I can play with. When I had the plus dot, 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 I couldn't play with that because I didn't know what all the things were. But now I can play with it. The temptation is to expand everything out and factorise it, and I'm not going to do that. Because remember, we know what we're trying to prove. We already know some of the factors that we want. And some of the factors that we want are already there. So it would be silly to expand this out only then to have to refactorise it back in. And the common factor I'm looking at there is 2k plus 1. And if you have a look at what we're trying to prove, 2k plus 1 is a factor. So let's take that out straight away. And then I'm just going to play with what's left. So if I take out 2k plus 1, I've got a third k, 2k minus 1, and 2k plus 1. And that's going to be a lot easier to work with now, because that's just a quadratic that I'm going to end up factorising. But in fact, there actually is another common factor there, which you might not see, and that common factor is 1/3. I can pull out the 1/3 as well, but that means the 2k plus 1 is now 3 times 2k plus 1. Because the 2k plus 1, if you like, what I'm saying is I could have written that as 1/3 times 3 times 2k plus 1, pulling out the common factor of 1/3. Why do I do that? Only because I hate playing with fractions, I suppose. So I pulled the fraction out, and I've now got a lovely little quadratic to factorise, and no surprises, we can guess what that's going to be because we know what we're trying to prove. Oh look, it factorises to be k plus 1, 2k plus 3. You don't have to waste time trying to factorise, I guess is what I'm saying, because we know where we're heading to. But you might want to just check and make sure it doesn't go 3 times what, oh yeah, that is 3. Yep, oh good. I haven't made a silly mistake somewhere. But yeah, you don't have to spend a whole heap of time working out, oh, what's this factorisation? I mean, you know what it should be. Okay? So I've proven it. However, it's only true if it's also true for n equals k. And that's when the next step comes in. Oh, well, hang on a sec. I proved it was true for n equals 1. So therefore, it must also be true for every other positive number by induction. And there's our proof. So that's the idea of an inductive proof. Let's have a look at another one. This time I've used some notation on the left-hand side. So rather than writing out all the terms, we write, okay, there's the general term. And we're going to go from the first term up to, well, n, whatever n happens to be. And we want to prove that sum will always be n on 2n plus 1. Now, what I do like to do sometimes is to rewrite it without the sum notation so I can get a feel for what the pattern is if I don't see it straight away. So if I did, and notice I haven't gone 1 times 3 is 3 and made it 3, 3 times 5 is 15. I've left it as the multiplication so I can see the pattern of what's happening there. So the first term would be 1 on 1 times 3, then 1 on 3 times 5. And then, okay, what we're doing is we're multiplying consecutive odd numbers in the denominator. All right, well, let's test it. Is it true for n equals 1? Well, the left-hand side, as I say, the first term would be 1 on 1 times 3, which is 1/3. Right-hand side, if we put that into the formula, yes, we get 1/3. So, great, it does work for the first term. So I'm going to assume it's true for n equals k. Now, I've written it out, all the terms, rather than the sum notation. Okay? But I suppose if you were going to use the sum notation, you would be writing k equals 1 to k, which is a bit odd. when you're substituting in for k. You might want to change the k to an r or another letter. I mean, it doesn't really matter, but so you don't get confused of which k is which. We're going to prove for k plus 1. So there's the next term, 1 on 2k plus 1, 2k plus 3. We'll end up getting k plus 1 on 2k plus 3, hopefully. Okay, here's the proof. But again, it's a series type. So I'll rewrite it as the sum to k terms plus the k plus 1th term. And the sum to k terms we've assumed was k on 2k plus 1. So now I've just got an algebraic fraction to play with. Now we're trying to prove, I'm just having a look at the denominator, we want to prove it's 2k plus 3. I've got that in the second fraction. I guess it makes sense to make this just one complete fraction. Fortunately, 2k plus 1 is already common in both. So the first fraction, I just need to multiply top and bottom by 2k plus 3. So now, again, because I see what the answer has to be, I'm thinking that magically the top of this fraction will be, I don't know, k plus 1 outside of 2k plus 1. But of course, to just write that for my next step, I could be accused of fudging, which of course I just did. So you sort of need to put the working out there so you can see. So the top of the fraction becomes 2k squared plus 3k plus 1. This is where we can fudge. Oh, I wonder what that is, factorise. Oh, look, k plus 1, 2k plus 1. And now the 2k plus 1's cancel. Oh, yes, excellent. I get what it is that I'm looking for. But again, just check. You might have made a little silly mistake in there somewhere. Make sure it does work. So yes, that cancels. So you little beauty, works for k plus 1 if it works for k. Well, I went and proved it was true for 1, so therefore it's got to be true for all the others by induction. So let's have a go at some of those. Number 10 is interesting in the book in that it's actually a question on polygons. So it's not writing out terms. You've got to think about, how am I going to present my solution here? It's still the same idea. You might use diagrams, but still using the same idea.